Lesson 37, Unit 7-1, page 421, Part 2. We're going over the homework sheet. The directions for number 5 and 6 say, express each value as a trigonometric function of an angle in quadrant 1. Now, we're going to name the function of an angle in quadrant 1. Now, what is that trying to tell us? That it's between 0 and 90 degrees. In other words, an acute angle, right? We're going to find the acute reference angle for that. But we don't want to change the value. So my answer may be the positive of that acute angle, or it may be the negative of that acute angle. Now, I'm saying that to say this could confuse you. You might think, oh, quadrant 1, it has to be positive because everything's positive. No. We actually want the value of what they gave us, cosine 27 pi over 8. But we want it in terms of an angle from quadrant 1. It may be the negative of the angle from quadrant 1, and it may be the positive of the angle from quadrant 1. So we're going to give it the sign of whatever quadrant it lands in. We're going to give it the name of the angle associated with that in quadrant 1. That makes sense. Anyway, okay, so what are we going to do? Well, we got to take out circles and half circles, and we're talking about eighths. So how many eighths does it take to make a whole circle 2 pi? It takes 16 eighths to make a 2 pi. So we can take out a 16/8. Let's just do the subtraction here so we don't miss it. 27 pi over 8 minus 16 pi over 8 leaves me with 11 pi over 8. So when I take out a circle, I've taken out of 27 pi over 8, 16 pi over 8. That leaves me with 11 pi over 8. Okay, now, a half a circle is what in terms of eighths? 8 eighths. So then I think, well, can I take out a half a circle, which is pi? Yes, so now I can say, well, 11, pi over 8 minus 8 pi over 8 leaves me with 3 pi over 8. Now, that's gotten it down smaller than a semicircle. So now I'm down to something that's in quadrant 1, right? Now, unless I'm over a half, because a half, you see, I could actually take out, how much is a half of a semicircle? Well, that would be, in terms of eighths, that would be 4 pi over 8, and that would be pi over 2, because I've got to be even less than 90 degrees. So if I could take out a 4 pi over 8, I'd take it out too, so I end up in quadrant 1. But I can't do that, so I took out a whole circle, I took out a half a circle, and I got down to something in quadrant 1. So we're going to write it as cosine of 3 pi over 8. But then I got to think, where did I land after all that taking out? Where did I actually land? Well, if I went all the way around, and then I went halfway around, are you seeing what really happened? And then I go 3 pi over 8 more, I actually ended up in quadrant 3, didn't I? That's where 27 pi over 8 really ends up. Now, we wrote it in terms of an acute angle from quadrant 1. But when we do our A Smart Trig class thing, we realize that what is positive in quadrant 3 is tangent, and so this angle is the negative of cosine 3 pi over 8. Now, the cosine 3 pi over 8 is the angle that this connects with in quadrant 1, the reference angle. But it's the negative of that because it landed in quadrant 3 for real. That make sense? Hope I explained that good. That's crazy. Yes. Negative cosine 3 pi over 8. All right. The question was, this is a good question. I want to repeat that question. The question was, could you have said cosine negative 3 pi over 8? Now, there's an identity about that, remember? The opposite identities. Remember we said that? And what did we say about those opposite identities? We said that sine of negative theta is the same as negative sine theta, or was it? And then we said that cosine of negative theta is equal to negative cosine theta. And so we're not sure, so look at your chart and tell me which one's right. It's in your memory work. The opposite identities. It's in your textbook on page, it's in your textbook on page 426. On page 426, sine negative A is the same as negative sine A. Cosine negative A is the same as cosine A. So sine negative A is equal to negative sine A. That one's correct. Cosine of negative theta is equal to cosine theta. So the question was, could we take that negative and put it there on cosine? And the answer is no, because of the opposite identity. Had that been sine, could you have? Yes. But it was a good question. It brought up something else that we needed to learn. We talked about why in the last video, right? Because, remember, when you go from sine to of theta to sine negative theta, let me draw the picture for you. If we say sine negative theta, what are we really doing? We're going clockwise, which puts us in quadrant 4. In quadrant 4, sine is negative. See how come? And then we talked about the cosine. We said if we write cosine negative theta, that really means to go clockwise, which puts us in quadrant 4. And in quadrant 4, cosine is positive. So sine negative theta is the negative of sine theta, and cosine negative theta is the positive of cosine theta. So again, that's where it came from. But that was a good question that brought us to some other stuff we learned before. All right. Any questions on that? All right. So we do have to be specific how we write that. All right. Let's take all those things out of there. I guess we can take all of this out and start over with number 6. Hopefully we're getting this down. This is going to help us a little bit for the last test we took. Some of you had a little bit of trouble with some of that. We have cotangent of negative 660 degrees. Now, we're actually going to be going clockwise, right? So we're going to take out circles going clockwise. How many degrees is a circle? How many 360s can you take out of 660? So if we said negative 660 plus 360, you would have negative 300, right? So we've gone all the way around. You can't take another all the way around out, so we're going to take out a halfway around. And that leaves us with 120 negative. We got to get down to an acute angle, right? So we need to take out a 90 now, a fourth of a way around. And we end up with negative 30. Now 30 would be in quadrant 1. Okay? And so we're going to take this out and take this out and take this out And did I make a mistake? 3, 1, yeah, no. I made a mistake in my notes in my books where I made the mistake. I didn't make a mistake here. Okay, so I wrote things backwards. Anyway, so we got 30. So it's kind of like, notice that last little minus 30 part. We took out the whole circle. We took out a half a circle. We took out a 90, and we had 30 left. Oh, I didn't mess up. We took out 30, and we're going backwards. But what angle does that leave us with? Ah. So we ended up, if you think about the positive, right, quadrant 1, the reference angle then would be 60 degrees. And so from quadrant 1, thinking about an angle in standard position, this would relate to cotangent of 60 degrees. Now we're in quadrant 1, and in quadrant 1, this original angle would have been positive because it landed in quadrant 1. So we're going to have cotangent 60 degrees. Any questions on that? You might be tempted to take the 30, but you were going backwards, so your reference was really the 60, okay? It's got to be an angle in standard position when we name that last angle. Any questions on that? All right, number 7. Now, what we're going to do here is simplify expressions using all of our trigonometric identities, okay? And so we've got the reciprocal identities, the ratio or quotient identities. We have the Pythagorean identities, and then we have the opposite angle identities, okay? So we're going to start doing some of these, and it's a little bit crazy what can happen in this. There's just so much stuff that can happen. And you have to have memorized your stuff, kind of, sort of. If you haven't memorized your stuff, it's really going to be hard to think through this. Because you're going to have your chart, and you're going to go, okay, what could I do with this? But if you already have it in your mind, you can think about what I could do with this easier. Now, if we think about this complex situation, what we want to do is simplify. So we want to try to write it all in terms of sine and cosine and make stuff cancel. That's what we're trying to do. And what's going to happen here is we're going to start using a lot of fraction rules, simplifying fractions, and unsimplifying fractions. I know that sounds crazy. I want to say his name. There you go. Okay. Thank you. So what we're going to do is unsimplify. And when you get to calculus, you're going to do a ton of that. We spent most of our mathematical careers putting things in simplest form. In calculus, just to make things work, we make them not be in simplest form, just so we can deal with them. So that's going to be hard for you to do, but that's just what's going to happen. Now, we know that cotangent is the same as what if we wrote it as a ratio. It's cosine over sine. Now, this material that we're talking about, anything we say is on your little sheet there, okay, that you really need to memorize. And so we know that tangent was sine over cosine, and so cotangent is cosine over sine, and this is the wrong sheet that I have in my hand, but you've got a sheet, there it is, where you have the ratio identity. If you see at the top left of your little sheet I gave you, we have cotangent theta is cosine theta over sine theta. So if we change the numerator to that and leave the denominator the same, then we can find a canceling opportunity when we actually do the division. To divide by, see, this is like cosine over 1, right? So we have a fraction divided by a fraction. Now, how do you divide fractions? You multiply by the reciprocal. So we have cosine theta over sine theta. Our fraction bar was divide. We're going to change that division to multiplication, And we're going to take this fraction that we were dividing by, and we're going to multiply by its reciprocal 1 over cosine theta. And that creates a canceling opportunity for us. Okay? So we're using identities to make substitutions with, and that's going to create some simplifying opportunities for us. Now, at this point, you can see that the cosines are going to cancel, and you're going to have 1 over sine theta. Using our reciprocal identity, we know that the reciprocal of sine is cosecant. So in simplest form, cotangent theta over cosine theta simplifies to cosecant theta. To simplify, we used a ratio identity, and then we used a reciprocal identity, and between that we used some basic fraction rules. To divide by a fraction, you multiply by the reciprocal. You're going to find out we're going to use a lot of fraction rules. This is why math teachers get frustrated when in Algebra 1 you're punching the calculator all the time instead of learning your fraction rules. And you really have to know them as you move up the line. Okay? All right. Now, I'm going to go ahead and do number 8, and then I'm just going to show you some tricks that are applied to nothing that you're going to apply to something later. Okay? Okay, so let's look at number 8. Number 8, we had sine x plus cosine x quantity square plus sine x minus cosine x quantity square. Now, what we have is a binomial square plus a binomial square. We're getting back into pure algebra 1 now. Everybody make sure you're paying attention. This isn't a piece of cake, obviously. Remember that when you do a binomial square, you could do the full method. You could write this out twice and then first, outer, inner, last if you're a full method person. Or you could say, if you know the concept of squaring a binomial, you could take the first one square plus 2 times the product of them plus the second one squared. And if it was a minus in the middle, you would have the first one squared minus 2 times the product plus the second one squared. Now, those are the formulas for expanding a binomial square, being a plus or a minus. Again, you could also do the full method. Write it twice, first, outer, inner, last. Okay? But we should have somewhere in Algebra 2 and pre-calculus at the front have dealt with binomial squares. You probably completed the square at one time to get good equations for circles and things. Yes. This is a binomial square, and this is the formula for squaring a binomial. This again is a binomial square, and that's the formula if it's got a minus in it, and the formula if it's got a plus in it. You could just put plus 2ab either way because the sign rules are going to take care of the minus, so you really only need one formula. Okay? So it's the formula for squaring a binomial. It actually looks like this: a plus b quantity square is equal to a squared plus 2ab plus b squared. If there's a minus in there, it's just going to put a minus in the middle. Sign rules are going to take care of that. Okay, so we're going to have the first one, sine x. Now let me tell you something. Sine x squared, that's not how we usually write it. We write it like this, sine square x, but it means sine x squared. Okay? We just write it as sine square x. And then we're going to have plus 2 sine x cosine x, 2 times AB, the product of them. First one squared, plus 2 times the product, plus the second one squared, and the second one is cosine square x. Okay? When we square the second one, we're going to have plus sine square x minus 2 sine x cosine x plus cosine square x. So the first thing we're going to do you notice we're following, please excuse my dear Aunt Sally. We just did exponents. You couldn't do what's in the parentheses because they're not like terms. So we went to exponents, and we did the exponent. We expanded the binomial. Now we're going to combine like terms. We're going to add or subtract. We always use order of operations. Now, notice that we have a plus 2 sine x cosine x and a minus 2 sine x cosine x, and those are going to cancel. And we're going to combine like terms, and we have a sine square x and another sine square x. And so we have 2 sine square x. And then we have a cosine square x and a cosine square x, and so we have plus 2 cosine square x. Understand that? And because, yes, because of our algebra skills, we see a common factor, right? We could have left them separated and seen 2 Pythagorean identities sitting there, but we could also look at it like this and say, okay, we can factor out that common factor 2, and that's really no different than saying, well, we saw 2 of those little Pythagorean identities sitting there. We just said it a different way by factoring, right? You could have said, I see a sine square plus cosine squared, and we know that that's 1. And I see a second sine square plus cosine squared, and I know that's 1. But algebraically, we have 2 of those, which is still that. Now, right here, we have a Pythagorean identity. And again, y'all are new to this game, and so you're just going to have to go to your chart and look at every little step for a while and just say, is that something special? You know, is there anything special about this mess I've created? Well, there is, because your first Pythagorean identity says that sine square theta plus cosine square theta is equal to what? 1. So that big mess in yellow turns into a plain old 1. And so we have 2 times 1. Now, you realize that even though you're going to have a calculator and even though you're going to have a sheet full of rules, you're not going to be able to do this if you don't study that sheet full of rules. Because you're going to have so many things to look for, you're not even going to know to look for them if you're not somewhat familiar. This sheet is to remind you of exactly what it looks like. If you haven't studied it enough to know it looks something like what you've got, it's not going to do you much good. Okay? Be like looking for a needle in a haystack, and you only have so much time to do it. Okay? And so 2 times 1 is 2, and so the answer is 2. Any questions on that? Now, I need to talk about some stuff that can happen. In middle school math, we said 3/4 is in simplest form, and we would never let you write something as 6/8. Or we would never let you write that as 30/40. But we've already fudged on that way back in Algebra 1. You remember in Algebra 1 when we were graphing? And this might be like 100, 200, 300. And we had a slope of 3/4, and we're like, we can't see how to go up 3. So we're just going to enlarge our slope by multiplying, and we'll get 300/400. And now we can say, oh, I'm going to go up 300 and I can see how to do that. So in application, sometimes simplest form doesn't work very well. Well, that's going to keep happening more and more and more as you get into college algebra level, college trig level, calculus level. We're going to unsimplify. Now, there's some tricky ways to do that. Let's talk about that. Y'all watch this. Y'all really do need to hear this, even if you don't think you do. Let's say that we had 3x plus 4 is equal to 12. If I wanted to solve, I would undo addition by subtraction. We did it to both sides. That's what I'm wanting you to visualize. And we would get 8, and then we would undo multiplication by division, and we would get x is equal to 8/3. Now, we can do anything we want to do as long as we do it to both sides. I could take a deal like x is equal to 4, and I could say, well, I want to make it look a certain way. Let's say I want to make that look like 3x plus 6, but all I've got is an x. So what can I do to make the left side look like 3x plus 6 and it still be equal? Keep its identity. You see what I'm saying? Well, we could say, well, I could multiply both sides by 3. If I multiply this by 3 and that by 3, then I've got 3x is equal to 12, and it's still equivalent. The value of x is still 4, but it looks more like what I wanted to have. We unsimplified to try to make what we have look like what we want. And we can say, well, what else could I do? Well, I could add 6 to both sides. And if I did, I would get 3x plus 6 is equal to 18, and the value of x is still 4. It just looks different. And so I unsimplified to make that x side look like I wanted it to look. That's opposite of what we've ever done in math. But you're going to have to do that in trig to simplify these things. So you may have something like sine square. Let's just say you had sines. Let me do something right here. See, you got sine square plus cosine square equal 1, right? So let's just say that I wanted something, if I move that over there, I would have cosine square equal 1 minus sine square. Let's just say I wanted to turn a sine square into a 1 minus sine square, okay? Now, y'all watch this, because we're playing around with an identity here. Y'all hang with me. You may think this is nuts, but this is important. How can I make, I'm going to put it up here, how can I make sine square theta look like 1 minus sine square theta? Now, I don't care what's on the other side, because we're not trying to figure that out right now. We're just playing with stuff. What could you do? How could you get a 1? You could do a plus 1 minus 1 plus sine square theta. What have I done to the left side? I added 0. Plus 1 minus 1, 0. I added nothing over there, but I got something that looks kind of like what I had. See how tricky that is? That's pretty cool. Now, what if I said, well, you know, I think I'll just factor out a negative 1 right here. Let me factor out a negative 1. If I factored out a negative 1 right here, I would have negative 1 times 1 minus sine square theta. So now I've got a 1 minus 1 minus sine square theta. Well, that's what I was trying to get. That's kind of tricky, wasn't it? See what I did? I'm going to show you what I did again. Now, see, I don't know what's over here, but what's over here, when you go plus 1 minus 1, you don't have to do anything over there. When you factor out over here, you don't have to do anything over there. But if you wanted to get this by itself, you could now subtract 1 from whatever's over there. And then you could, after that, divide by negative 1, and that thing would be all by itself. You see? It doesn't matter what's over there. I just wanted to make that side look like I wanted to make it look, you see. Okay? Let's talk about that again. Here's where we started. We started with sine square theta equal. Now, Andrew already knows how important this is because he's already done all the homework in college trig, and he's had to mess with this, and he's been in here for tutoring, and we've been figuring these little tricks out. Sine square theta. We want to get a 1 minus sine square theta. We're trying to turn this into that. And you look at it and say, that's impossible. And you go through all your little identities here, and you're not going to get it done. It is an identity, but we need to mathematically trick it into looking like that. So we say, well, why doesn't it look like I want it to look? Well, because this one's got a 1 and that one don't. Well, how can I get a 1? I just stick a 1 there. But if I'm going to make it equal, I got to put a minus 1 also. So I've really done nothing, because 1 minus 1 is nothing. I just changed the looks of it, but it's still equivalent. And then I say, well, but I'd really like for there to be a negative right there. Say, well, that's fine. All you have to do is group that, because that's kind of starting to look like that. But the 1's the wrong sign, and the sign is the wrong sign. And to change a sign, all I got to do is factor out a negative 1. And that changes the sign, and put my 1 back. And now what's in there looks just like what I was looking for. Okay? This is the kind of stuff that you're going to have to do, which says that this sheet is not near all you need to be able to do. You can have this sheet in the calculator, and this test still going to be kind of hard. Okay? We're understanding what's happening. And then if you wanted to get that all by itself, you would subtract 1 from both sides, and that would disappear. And then you would divide by negative 1, and that would disappear. And then on the left side, you would have what you're looking for, 1 minus sine square theta. Okay? If we had something like sine square theta over cosine square theta over cosecant theta over cosine square theta. I'm just making junk up. I don't even know what I'm doing. Then how could you make, what's the first thing you could do to make that simpler? Y'all need to be watching what I'm doing. I'm just making junk up so you can see some tricks. What do we not like about that? We don't like the fact that it's got a denominator, right? We don't like that denominator. It's a complex fraction. Well, notice that it's actually a common denominator. If we actually were to multiply the numerator by that denominator and multiply the denominator by that common denominator, then it would cancel here and cancel here, and we would have sine square theta over cosecant theta, and it actually looks a little better already. And then we can say, well, we know what cosecant is. That's actually what? It's actually the reciprocal of sine, so all that does is throws another sign on top, right? And so it simplifies to sine cube theta. And I just made that up just to throw something up there. I wanted you to see that common denominator in your numerator and denominator, and you can multiply through by the common denominator and eliminate the denominators. So this is the kind of stuff that's going to go on. All right, any questions on that? I'm going to stop there, and we'll have some work time. And as you do problems and get stuck, I'll come to the board, and we'll talk about the tricks it takes to make it happen.